Hello, Mr. Hafiza. My name is Susanto Darren, and my student ID is CST2509108. And in this presentation, I will be taking you through our complete design implementation of our question 1 doubly linked list for the assignment 2. I'll explain the node structure, walk through how each core function works, and demonstrate our program's behavior using the output. Let's jump into the code. So, to begin, let's look at our node structure, which we define using the typedef feature. So we can see from here. And then unlike a basic singly linked list, where you can only transverse forward, a doubly linked list requires us to navigate in both directions. To achieve this, our node structure contains three distinct parts, which the first one is the data, where we put as an integer. Next is the pointer, which is pointing to previous, and then the pointer pointing to next. So, to make the program easier to manage, we also created a wrapper structure called doubly linked list that simply holds the pointer to our head node. Passing this wrapper structure by reference keeps our function parameters in clean. Okay, so now let's break down the logic behind our operations. First, we have is empty. Let's see the function. So this is the isEmpty function. This is a quick helper function that evaluates whether the list head pointer is null. If it is, it returns true. We use this check as a safety guard at the start of our operations to prevent the program from trying to read non-existent memory. Then the second function is we have insert node. So the prompt specifies that every new node must be inserted at the beginning of the list. To do this, we dynamically allocate memory on the heap using malloc. Once allocated, we set the new node's data, set its previous pointer to null, and point its next pointer to the existing head. Also, if the list is not empty, we must update the old head previous pointer to link back to our new node. Finally, we update our main head pointer to point to this new node. Okay, so the next function, we have the find node. So to search for a value, we transverse the list using a while loop, and then we initialize a counter called position at 1, as we can see from this one. And then in the while loop, as we go through the loop, the nodes using current equals to current to next, then we increment our position tracker. If we find a match, we print the exact position and break out the loop early. If we reach the end of the list and hit null without finding it, we output a clear message stating the value was not found, as we can see from this one. And then the next function is delete node. So this function handles the removal of the first occurrence of the target value. We first transverse the list to locate the target node. Once found, we bypass it by updating the neighbor pointers. So, if first we redirect the previous node's next pointer to skip the target and point directly to the target's next node. And then we redirect the next node previous pointer to point back to the target's previous node. If the node being deleted is the head node, we simply shift the main head pointer to the next node in the sequence. Once the pointers are updated and the node is fully isolated, we call free the node to release the memory. And then lastly, we have the function display list. So we loop through the entire list starting from the head. To match the required visual output perfectly, we print null at the boundaries and use arrows to show the connections between the nodes to show the output. And then we will jump into the edge case handling. We ensure that the program behaves gracefully in every scenario. The first one is empty list, as I explained before. If you try to search or delete when the list is completely empty, our program detects this immediately using isEmpty function, instead of crashing or pointing to an invalid memory. And the second one is single node list. When deleting the only node in the list, our deletion logic notices that there are no neighboring nodes. It safety updates the main head pointer into null. and then reverting the list into a clean empty state. Next one is the invalid value. If a user attempts to search or delete a value that does not exist in the list, our loop safely transfers until they hit the terminal null pointer. The programs catch this, avoid making any incorrect pointer updates. And that's all for the codes. Now let's jump into the output. Okay, so this is the output. First, uh, we program checks the list and prints that the linked list is empty because the start is empty, right? And then the the output asks us to enter three integers into the linked list, which then we will enter 30, 20, and 10. And then it will show that the linked list is showing from 30, 20, from null, 10, 20, 30, and then null again. And then the program asks enter the integer that you want to search in the list. We can just try to hit 20, and then it will search into the program. The program successfully finds it at position 2. But then when we try to search, for example, we search 50, yep, the value 50 is not found on the list because our integers is only 30, 20, and 10. And then the program asks if you want to delete from the list. Next, we will try to delete the number 10. So by deleting number 10, we'll see that the 10 is out from the linked list, right? So it's from null, 20, 30 into null again. And then the program asks again when to delete from the list. If we just simply hit 30, 30 is also out from the list. So it's only left with a single node containing the number value 20. If we want to delete again the number value of 45, we can see that node with value 45 is not found because our linked list is only has the value 20. Finally, when we delete the number 20, the list is now empty again. And if we want to search, for example, number 10, the linked list is empty. And then the program ends because there is no value if we search 10. Okay, so to conclude task 1, question 1, I want to highlight our free list function right before the program terminates. This function sweeps through the list and frees every single active node from heap memory. Okay, so that's everything from me. Next, I will give it to Rafa to explain the question 2. Thank you.
Okay, hello, my name is Muhammad Rafa, CST 2509106, and today I will explain why linked lists are the preferred method of for implementing a stack. And okay, um, first let's ask the question, why use linked lists? The basic answer will be dynamic size. Okay, what exactly does that mean? A linked list can dynamically change its size by allocating or deallocating memory for nodes. And it grows and shrinks on demand using a system heap memory, using the system's heap memory. This is a massive advantage over arrays, which force you to occupy a contiguous, pre-reserved block of memory, whether you use all of those slots or not. And okay, I've made two scenarios here to show you why pushing and popping is done at the head instead of at the tail, which is basically a difference between efficiency and inefficiency. And now take a look at the first scenario. At the top of the diagram, uh, we have this top here. As you can see over here, top. And our top pointer sits above node 1. If we want to push a new node or if we want to pop node 1 off the stack, we have immediate direct access We don't have to look at node 2, node 3, node 4, whatever that is. We update the pointers in a single instant step. This is why pushing and popping at the head is guaranteed the most highly efficient operation. On the other hand, let's look at scenario B, where popping is done at the tail. For example, we want to delete node 4 at the tail. Our data structure rule states that preceding node 3, the node before node 4, must have its next pointer updated to null, 0. So it becomes the new end of the list. And let's look at the pop operation over here. If we want to delete node 4 at the tail, node 4 cannot look backwards. It can't look back. In a single linked list, the arrows only point forwards. As you can see, all these arrows point forwards. None of them have pointed back. And because of this, the CPU is forced to start at the very beginning of the list. Hop to node 1, node 2, then node 3, just to locate where the node that comes before our tail. As the list grows to thousands, hundreds of thousands of items, this sort of sequential checking takes longer and longer for it to do, which sort of like downs our speed, which is highly inefficient, which is why pushing and popping is done at the head. Now, next up, I have 4 functions that we will look into that sort of is the main operations of the stack. And first up, we have add. I will spare you all these unnecessary explanations I've written down and just give a simple explanation. So the analogy is you place a new clean tray directly on top of the existing stack. And basically the add functions takes a new item, puts it at the very top of the stack, and makes a new entry point. It's like adding a new tray that immediately becomes the first one you will see. And then next up, we have withdraw. The withdraw function removes the top item of from the stack and then grabs the data, update the top pointer to the next tray down, and cleans up whatever memory is left of the tray that you just took, so we don't have any clutter. It's clean. And next up, we have display. So as the name suggests, the display function is just an inspector of the stack, which it does a quick inspection. It starts at the top and looks at every item in the list one by one until we hit the bottom, and then prints out what it sees so we can check the status of our stack. And finally, we have counting. This is also self-explanatory next to display, which is basically a function that sort of performs an audit. It starts at the top and walks through the entire list, adding 1 to a counter it has for every item it finds, and then giving us the total size of the stack. It counts the amount of items in a stack, which is all it does. It just measures the size. And then if we put it all together, the simplification is add puts something to the top, and then withdraw takes the one at the top off, and display lets us see what's currently in the stack. And then counting tells us how many items are currently sitting there. And next up, we have sort of the UI that goes in the stack. So the infinite loop UI, it's just a while loop that goes on and on, which provides a text-based interface, which keeps the application running continuously, displaying many options and waiting for input until you explicitly command it to stop. And then we have the switch case dispatcher. The switch case acts as an efficient dispatcher, routing execution to the appropriate functions such as push, withdraw, display, based on the number of specifics selected by the user. So let's move on to the sort of the operations on how this goes down. And we start with pushing. For pushing, we followed a two-step rule. First, we link the new node to the current top, and then we move to the top marker to this new node. The sequence is vital. We have to if we move the marker first, we lose the rest of our stack, which would lead to a memory leak. And then for popping, next up popping, we do the opposite. We hold onto the current topic. We hold onto the current top in a temporary variable, and then we move our top marker to the node underneath. Then safely delete the old one. By following these specific steps, we guarantee the stack remains intact, no matter how many times we add or remove items. That's all for me. Thank you. So, to conclude our presentation, we've learned a lot of things such as doubly linked list and the stack implementation. And we've understand how dynamic memory allocation and pointer manipulation works. And we've learned to not focus on the problem. Instead, we figure out what solutions can possibly mitigate our issues. And one of those was the pointer integrity of like keeping track of the connections we had, especially the previous and next pointers in the W linked list, which was quite difficult for us to do, but we've overcome that. And we found out that a wrong assignment could break an entire chain, and we solved this by sketching our pointer logic on paper before coding, which ensures our linked updates remain accurate within our command. And also, we've learned memory safety, like handling how to delete nodes from an empty list or clearing a final node. And we found out that it often led to crashes and potentially memory loss. And we solved it by implementing this sort of defense by consistently using isEmpty, the isEmpty function, and also ensuring we properly remove some or free up memory by using the free function, and we ensure the program remains stable. And overall, this assignment has helped us to more of understand how to control things and mitigate issues. And thank you for listening.